Into our second day of optimization. So I have this warm-up for you, and I'm not going to, when I check your warm-up books, I wouldn't check either one of these days because you may have these in your warm-up book or you may not. Here is a surface area problem for a can on the AP exam. They don't give you any calculus formulas, but they will give you geometry ones. I mean, they won't give you a triangle or a square or a circle, but if a sphere or a pyramid or a cone or surface area, they would give you any of those formulas. So here they want to know the dimensions of a 1 liter can, and notice they will also give you the conversion. They don't expect you to memorize that 1 liter is 1,000 cubic centimeters. And it's a cylinder. What will use the least amount of material? So the surface area is, now of course this isn't too hard, I hope, to figure out. If you had to, right, that the area of, there's the top and the bottom of 2 circles, so pi r squared, there's the circle formula, and 2 of them, and then 2 pi r h. If you cut, right, if you take scissors and you cut this can here, you would, and then you would actually get a rectangle, right? If you spread it out. And if you think about it, when you go around this can, isn't this the circumference here? And isn't the circumference pi times the diameter? But isn't that 2 times the radius times pi? And then isn't this the height of the can? So that's where this part of the surface area formula comes in. This is just the area of a rectangle, where the length is 2 pi r and the height is h. And again, this is 2 circles, the top and bottom of the can. So anyway, if I want to set this up, I want to use the least amount of material. So of the surface area, my job is to minimize surface area. Since I'm minimizing or maximizing, this must be right, minimizing or maximizing must be an optimization. I'm doing minimizing, so I'm going to be looking for a derivative of the surface area. I'm going to look to set the derivative of the surface area equal to 0. I'm going to look for endpoints. Consider endpoints. I'm going to look for where the derivative is equal to 0, and since I'm minimizing, I want to change from my derivative to change from negative to positive, so I can show that my surface area is changing from decreasing to increasing, which of course would be a min. So this is my thought process. This is what I want to do after reading the problem. So now how do I go about setting that up? So this is what I just talked through. They call the lateral area, like the outside area of the can. But notice there's too many variables here. So one of my strategies before has always been, I need an area. Now this is really SA, right? The surface area. Right? When I've had area before, you know, I wrote it in terms of X. So, but here I have a radius, and I have a height. That's too many variables. That's 3 different variables, and I need to have 2. So I say to myself, I need some way to replace either R or H in terms of the other. Since I only have one H, I'll think about getting rid of that. Now they did give me some volume information, right? There was something in the problem about cubic centimeters. That's a volume issue. So why would they give me volume when we were talking about surface area? Well, with the volume, I can use the equation pi r squared h, replace 1,000 for volume, and I get an expression for h. So what am I going to do with that expression for h? Put it into the surface area equation, and notice now I have the area function, surface area function, in terms of just r. There's no h, so I can take the derivative of the area function with respect to r. Notice when I do a little algebra, the pi's cancel out. 2 of those r's canceled out, so I was left with that formula, which is really 2,000 times r to the negative 1. So when I take the derivative, bring the 2 down here, bring this 2 down in front, 4 pi r to the first. Remember, this was really r to the negative 1. You want to think about that, r to the negative 1. So I brought down the negative 1 in front, 2,000 r to the negative 2. I showed my calculator here because if I had a calculator, I could just put this right into my calculator at this point, right? At this point, without actually finding the derivative, I could go to the calculator, I could put 2 pi r squared plus 2,000 r to the negative 1, turn it off, have the calculator draw the graph of the derivative for me, and then find where the derivative was equal to 0. So if I had a calculator, I would just write, I wouldn't even need to write this down, right, the derivative rule, but I would have to write that I set the derivative equal to 0, and then at what r I found that at. Now I'm going to go ahead and go through the algebra that you can see how I found r, but it is not a nice number. So I would certainly use a calculator and get an approximation. I would also store, I would use on my calculator, and I would store this value in alpha r, right? Because 5.42 is an approximation. So what do? I go to my number line at this point, a prime. Remember, if I do have, since I have my, I'm assuming I do have my calculator, I didn't even actually need to find the derivative rule. I just put the area formula in, had the calculator graph the derivative, and then I found 4.2 blah 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 by finding the intercept, x-intercept of the area function. And then I saw the derivative change from negative, looked at the graph and saw negative to positive, meaning the surface area was decreasing to increasing. Remember that this was 0 at approximately 5.42. Then I took this number, but the answer to the question, I needed the dimensions. So I took this number and I took it over here to my height function, and I didn't actually plug in 5.42. I plugged in alpha r, and I got the height. Notice if I left my answer like this on my test, I would lose a point, possibly, because if I'm going to round on an AP exam, I have to leave what? How many? That's right, 3 places past the decimal. So that handout that I gave you, when was that? Whatever day that was, with the examples in it, I went through the last video, I went through 1, 2, and 3. So here is 4. How close to the semicircle, y equals 16 minus x squared, come to the point 1 comma root 3? And they've given me a hint to minimize not the distance, but the squared distance to the curve. And that's something you wouldn't think of, nor would I, the first time I did problems like this. It's after I did some problems like this that I realized my math was just a little nicer with the squared distance instead of the distance. Because for the distance, if you look at the distance formula, gross, right? This is a semicircle. If you remember way back on the summer packet, I told you this equation. That is the, right, because there's a positive here, that's the actually an equation of a circle, but only the top half, because I only have the positive piece of the radical instead of positive and negative. So, and it has a radius of 4, so I go up 4 to the right 4 to the left 4. So where is the point 1 comma negative, root 3? Well, that's about here maybe. Right, that's 1 comma root 3. So how close is the semicircle to this point? Well, I see it, right? The shortest distance is there. So that is the distance I'm looking for. and I'm looking for that point. So I go to the distance formula. Formula is just Pythagoras, right? So it is the sum of the distances. Well, remember this x is 1, so how far is it to the x-coordinate? X-coordinate minus 1 plus, right, the y height from root 3. So there's the point 1, there's the point 13, here's the x-coordinate, and here, right, convince yourself that that is the y-coordinate. Right? How do you find out the height of any point at any x? You go to the equation and you plug in an x. This right here, so this is just the distance formula, right? x1 minus x2 squared plus y1 minus y2 squared. So if I call this my x2 and y2, this is my x1 and that's my y1. But again, how do I find a y height if the y is on the semicircle? I plug in the corresponding x. So I could take the derivative of this expression, but it would be kind of, I would have a lot of crap to do because I have that radical. So if instead I just square both sides, so I have d squared is equal to this expression. Notice I still have some chain rule issues, but this radical is gone. I just have to remember that I'm taking the square of the distance when I'm all done. Here's a picture of the parabola and the distance and the squared distance. So there is me expanding so that I don't have to do too much chain rule stuff. I squared x minus 1 squared, got x squared minus 2x plus 1, and then I squared this expression. When you square, remember this is actually just a radical, right? So when I square the first term, I do just get 16 minus x squared. But then I have to multiply 16 minus x squared, square root of, times negative root 3, and double it. So that's where this middle term comes in. 2 times the square root of 48 minus 3x squared. And again, try to figure out through the algebra, as to where that came from. And then square root 3, and I get, of course, 3. Collecting like terms, I get negative 2x plus 20 minus 2 root 48 minus 3x squared. Now finally I'm freaking ready to take the derivative. Taking the derivative with respect to x of the left and the right. The derivative of negative 2x is just negative 2. The derivative of 20 is 0. And the derivative of this thing, and again now I kind of put my power back and think of the 1/2. Taking the derivative there, I bring the 1/2 down. And I get 1. Then I get 48 minus 3x squared to the negative 1/2. And that's how the 48 minus 3x squared comes. And then, what do I have to remember to do? I need to take the derivative of the inside. And the derivative of the inside is negative 6x. And remember, this was a negative out here. And I just had a 1 on the numerator, so that's why I end up with positive 6x on top. Now, I did all of this. I got, what did I do? I want to minimize something. To minimize something, I needed to get an equation. in terms of one variable. Check, check. Then the rest of this crap was algebra, just cleaning up the equation. Then I finally did some calculus by taking the derivative, not forgetting the chain rule. So when I want to minimize something, my goal, get an equation in terms of one variable, take the first derivative, and then what? Set the derivative equal to 0 and solve for the x. So I move the 2 over and then multiply by that radical, divided both sides by 2, squared both sides. Oh, looky there, how nice. Now since I'm talking a distance, right, I don't need the negative, negative 2. So again, notice in the picture that where x is equal to 2, that is a minimum on both. D and d squared. So my endpoints here, of course the endpoints of the semicircle, -4 and 4. Actually, I guess I probably should call that 0, right? Because we're not talking about going to the other side. So here's my derivative. I need to see when my derivative changes from negative to positive. So I pick a number below 2, like 1. Right? Plug in 1. I will get a negative. Plug in something above 2, like 3. And sure enough, I get a positive. This is when the derivative of d squared, the d squared derivative on top. So what can I say about d squared? The distance squared changes from decreasing to increasing, therefore x equals 2 is indeed a minimum. So I just found the x. They wanted me to, now how close does that semicircle come? So I need to take 2 and take it to what equation? I want to find a distance. So where do I take this 2? Whoops, sorry. I take this 2, but I don't put it into the d squared equation, right? I put it into the distance. Remember that original distance equation, which is the radical of 2 minus 1 squared plus the square root of 16 minus 2 squared minus radical 3 all squared. And that, believe it or not, comes out 2 by 2. So I would not give this problem to you on a test without giving you this hint. This then, therefore, would probably not be on an AP exam written just like this, but I like it for bringing in the distance formula, minima, and showing you to square the distance, the whole trick of using the squared distance just to make my calculus a little nicer. I just thought it was a cool problem. Alright, here we go back to boxes. Now I had to say I was at a conference yesterday and talking with all these really cool engineers in the space and renewable energy and health fields, and I can't tell you how much optimization came up. They were talking about optimizing orbits for satellites and optimizing the distance of, from radiation to tumors, and just all kinds of these things. So yes, in AP first year high school calculus, when you're talking about optimizing distances to parabolas and volumes of boxes and things like that, but if you do this now, the optimization of really cool stuff is something that you can access in the future. Oh, I sound like a super nerd now, but anyhow, let's do this closed box. So as I read this, the material, the top of the bottom, blah, 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 I've got cost, material cost, and I have the sides, and a square base, find the dimensions of the box will lead to the, minimum total cost. So what do I want to do? I want a cost equation with one variable. Then I'm going to take the derivative of that cost, set that derivative equal to 0, do a number line, and since I want to minimize, I want to see where the derivative changes from negative to positive. So this is my game plan. So the first thing I have to do is come up with some equations. Where did that come from? Good. Think this is certainly a squared and this is the first, which means this whole thing is cubic. 16,000 goes with what? Volume. So I have a volume equation. Is that what I was after? I think not. Remember, I was after cost. But I started with the first piece of information they gave me, which was volume. So I used that number. Where the hee-haw did that come from? So I certainly needed cost, right? So I see a 3. So let's back this up a little bit. The top and the bottom cost $3 per square inch. So if I say this is x, and if you're looking at my volume equation, that's y, right? So x times y is the volume, which again is 16,000. So if I want cost, it's $3 per square inch. So $3 for my square, that's 3x squared. Well, where the heck did the 6 come from? Oh, right. I have a top and a bottom, so that's 2 of them. Then I'm going to add, hey, what's x times y? X times y. Oh, that's a side. How many sides do I have? 1, 2, 3, 4. Well, I have 4 xy's. So how come that's a square? That's 6. Oh, I forgot the freaking cost this time. 1.5 for the sides. So what is, I have 4 sides, but each side costs $1.50. So 4 times 1.5 times xy, there's my 6xy. So that's how I built this equation. I just didn't pop this cost equation. I know it looked on the slide, but that just didn't come out of the air. 6x squared plus 6xy. I had to take this whole box apart to get that cost equation. Now, once I have a cost equation, I'm ready to do the derivative. Oh, no, I'm not. I have x, and I have x, and I have who is not invited to the party. Y, not invited to the party. How can I get rid of y? I knew I was going to need this for something, right? So, y is equal to, right? Now, take what y is equal to in terms of x and put that here. And then you have an equation that is just cost, that is for cost in terms of just one variable. So, my cost equation Looks like that. Simplifies to right, because I have x squared here and x, so I just have 1. Now look how much time that took, and I haven't done any calculus. And that's what's hard for kids on assessments, is that they can't get to the calculus. The words, the setup, coming up with their own equation, recognizing that I actually needed 2 equations when I have 2 variables so that I can substitute and get to 1 equation with only 1 unknown. Because once you're here, once you're finally, whew, right, you never thought you'd hear that. Oh my God, thank God I'm at the calculus part. Because now, what do I do with the cost? I am just going to take its derivative. Remember, that's 96,000 x to the negative 1. What do I do once I find the derivative? You got it. Set it equal to 0. Now you can tell this is a math book because, shocker, what happens here? Woo! An integer. So the derivative of cost was 0 at 20. I go to my derivative equation here. I put a number in below 20. I see that this is negative. Above 20, the first derivative is positive. Therefore, the cost must be changing from decreasing to increasing, meaning 20 is a minimum. Did I answer the question? I don't know. They asked me what is the minimum cost, so I have to take 20 and plug it into my cost equation. Uh-oh, I need a y. How do I know what y is? I know x is 20. Oh, alright, I'm going to go with hello. Y is 16,000 over 20 squared, which is 40. Therefore, the minimum total cost is $7,200. Let's make a poster. So I am going to make a poster. Notice what poster I chose to display here, huh? You see that? So as I'm reading this, the words that come out at me are rectangle, 50 inches squared, so this is an area number, 4-inch margin at the top and bottom, and 2-inch margin at each side. What are the overall dimensions that I will minimize the amount of paper? So, I have two kind of issues going on here, right? I have an area, and then I have inches, which could also be are the sides, but what are they the sides of? Wait, I need to draw this out a little bit more. I mean, I might post my cute little poster thing is cute. Ha! Is nice. But let me do something I can mark up here. So, 4 inches at the top. So this margin here is 4. And the side margins are 2. So I'm designing I want 50 square inches of printing means that this part that area is 50. And 50, any area formula of a rectangle is length times width, right? Let me make that, I'm a boring math teacher, so I'm going to make that x times y. So, what do I have? If I have x times y, but that's the area of the little one, right? So what are but they want the overall dimensions, so of the large one. So if 50 is the area of the inside one, and x is this length here, if that's x, well, what is this length then? Well, let's think. There's 2 inches there, but doesn't that also mean that there's 2 inches there? So if this distance is x, isn't this distance x plus 2, which is x plus 4? So the area of the big rectangle, right, this is the area of the small rectangle. The area of the big rectangle isn't x for that side, it's x plus 4. Conversely, what is this side? That length, I know this length is y. Well, how much extra is here? So this is y, but isn't this a 4? And that's a 4, right? So I have y plus 4 plus 4, which is 8. So what is the overall dimensions that will minimize? Well, I now have an area formula for the big rectangle, and I want to minimize it. So I just have to find the derivative, right? I'm just going to take the derivative of the big, because I have the area of the big in terms of there's the x, but who is not invited to my derivative party? That gosh darn y. What am I going to do? How can I get rid of this y? Rewrite this y in terms of x. Here's a y. Can't you solve this equation? Of course you can. So let's go back over here and say, well, if the area of the small rectangle is 50, which is x times my y is the same thing as 50 over x, correct? So, not a prime yet, just regular a is x plus 4 times not y, but 50 over x plus 8. Let me do some algebra here. Still no calculus. X times 50 over x is just 50, right? Plus 8x plus 50 plus times 4 is 200 over x plus 4 times 8, which is 32, which means the area of the big rectangle is 82 plus 8x plus 200x to the negative 1. Now, look at all of this that was just set up in algebra. Now I'm going to go to the calculus and say, now that I have an equation that I want to minimize, and I only have one variable, I can now take the derivative of the big rectangle, and of course the derivative of 82 is nothing. The derivative of x is 8 minus 200x to the negative 2 And I'm going to set that derivative equal to 0. Move the 200x squared over here, multiply by x squared, so I will get 8x squared is equal to 200. Oh, look at that. Plus and minus 5, but again, I'm talking about dimensions of a rectangle, so I'm going to just say 5. Did I answer the question? No. Firstly, I found where the derivative is equal to 0. I'm pretty sure that's going to minimize, but on a calculus test you have to show. This time I'm going to use the second derivative. If this is the first derivative, I'm going to use the second derivative test. Just to show off, just because I can. So the derivative of 8 is 0. The derivative of negative 200x to the negative 2 is positive 400 over x to the negative 3, or over x cubed. And I'm going to take where the first derivative is equal to 0 at 5, and I'm going to plug that number into the second derivative. So I get 400 over 5 cubed, which I don't really care what that is, I just care that it's positive. Therefore, the first derivative was 0, meaning I had a horizontal tangent, and the second derivative at that same place was positive, meaning that I'm concave up. Therefore, by the second derivative test, I have a minimum. Did I answer the question? No. What overall dimensions? So they want the dimensions. I know that x is 5 and y is 50 over 5, which is 10. So the dimensions must be 5 and 10, correct? No. That is the dimension of the small area, but they wanted the overall dimension. So the overall dimensions are 5 plus what? 4. And 10 plus what? 8. Neat. Alright, last one. We're going to do a movie screen this time. A movie screen is on a wall that is 20 feet high and 10 feet above the floor. At what distance from the front of the room should you position yourself so that the viewing angle of the movie screen is as large as possible? So, at what distance so that an angle is maximized? So, I know I want to maximize, which means I want a derivative equal to 0, changing from positive to negative. So they did give me a hint this time. Write an expression for theta first and use it to write an expression for, alpha first, and here's an expression, and then write an expression for theta. So here's the drawing. This is the movie screen right here. So the movie screen is 20 feet high, but it is positioned 10 feet off the floor. That's right here. So of course I have a big triangle here, and the total height from floor to top of the movie screen is 30. This then is the ground, which is my distance from the movie screen. And this angle here, right, going from the ground all the way up, goes with 30, which is a right triangle. And can you see why they're suggesting that you think about angle alpha, even though that's not the angle you want? Think about that for a minute. has to do with the right angle again, right? So I have a right angle, and this smaller triangle is a right angle, just like the bigger triangle. Neither of which, of course, involve the angle that I'm after. But that triangle is not a right triangle. And I'm really comfortable with my right triangle. So let's see what I can do with right triangles. So the hint was to go ahead and write an expression, because remember, what I want is an equation with one variable. So the tangent of that angle that I'm not after is equal to the opposite side, 10, over the adjacent side, which is x. Now, do you agree that tangent of the big angle that I'm also not interested in, really, is not 10 but 30 over that same x? True? You see where I'm going here? So isn't it true that solving the first equation for alpha means I've got inverse tangent. Solving the second equation for the big angle means I have inverse tangent as well, but of a different expression. The angle I do care about, hello, is simply the big angle minus alpha. True? Oops, sorry. So I have an equation for theta, which is the big angle, represented by inverse tangent of 30 over x, minus the little angle, represented by inverse tangent of 10 over x. And when you have an expression, or an equation for what you want to minimize or maximize in terms of one variable, what do you do next? That's right, calculus. Oops, I wanted to change color, silly. So, the derivative with respect to x of theta is the derivative of a difference. But what is the derivative of a difference? Just the difference of the derivatives, right? Inverse tangent, grown or not, right? What's the derivative of inverse tangent? It is a fraction. 1 over any radicals? I think not. 1 plus the stuff squared. That's right. Don't forget the chain rule. Times the derivative of the stuff. That's 30x to the negative 1. So the derivative is negative 30 over x squared. Minus the derivative of inverse tangent, again, is 1 over 1 plus the stuff squared times the derivative of the stuff. That's really 10x to the negative 1, so its derivative is negative 10 over x squared. So let me do a little algebra on that expression. The derivative is negative 30 on top of x squared plus 900, and just do some, I'll leave that to you to do that algebra, minus a negative, so this becomes a plus, 10 over x squared plus 100. when I had the derivative, I set that equal to 0. Save myself some writing and just say I'm going to set that equal to 0. When I do that, I'm going to put 1 on each side, so we'll put 30 over x squared plus 900 equal to 10 over x squared plus 100. Cross multiply. Do some algebra. Actually, I think I'm going to divide both sides by 10 here, huh? So I get 3x squared plus 300 is equal to x squared plus 900. So therefore I have 2x squared is equal to, oh look how nice this ends up being, x squared is equal to, oh not as nice as I thought. X is equal to plus or minus, but again I'm dealing with distance, so I'll just keep plus square root of 300, which is what, 10 root 3. Am I done? I think not. Right? Once on a calculus test, you have to, once the derivative is equal to 0, you need to now I know I've been pretty cavalier with my endpoints, but when we're doing problems like this, endpoints end up meaning you don't have a box, or you don't have a distance, or you know. So I know I am being a little cavalier here when I've just lectured about making sure that you keep endpoints, and you should, right? 0 and whatever. So at 10 root 3, the derivative of theta was 0. So what does that say about theta? I tested values to the left and the right of 10 root 3, and I did get positive and negative, meaning that theta was increasing, and then changing to decreasing, meaning 10 root 3 must have been a maximum. Am I done? What did they want me to ask for? At what distance should I position yourself so that the angle is maximum? So I need to go and find the viewing angle being large, so I need to find x. I found x to be 10 root 3, did they give me? Feet, right? So this is 10 root 3 feet, but what is my largest angle? So I take theta back to this equation, and I get inverse tangent of 30 over 10 root 3, which shockingly reduces to 3 over root 3. Minus inverse tangent of 1 over root 3. So what angle has a tangent 3's of that? Well, that's pi over 3. And this is pi over 6. What is root 3 minus, pi over 3 minus pi over 6? Well, that's pi over 6, and of course that is radians, but normally when we talk degrees to people, when we're talking about viewing angles, we would say 30 degrees. Right? Alright, so there's me just going through a bunch of problems with you. Your homework. Is there? Homework number 7, and finish these handouts that even if you redo problems, it helps, I promise. So I know this is a lot of problems to do. I have the key in class, and you'll have the weekend also to keep working on these and seeing. Again, I'm sure you'll find that your struggles are in the setup, not the calculus. So just the more problems you can do, the better. Have a good evening and a great weekend.